time we kind of gave the final touch of the magnetostatics. So we did electrostatics, we did the magnetostatics, and now we are moving to a new regime where the fields are changing as a function of time. And now, the moment that we have the electric field and the magnetic field changing as a function of time, then we can, what's the name? We can figure out that the fields, the electric field and the magnetic field, they are coupled, okay? So we did electrostatics, magnetostatics, but now, so in these two domains, we had that the electric field, it was not a function of time. Magnetic field, it was not a function of time. This is what we mean with this. But the moment that the electric field is a function of time, then we can say that we can have some induced magnetic field which is going to be different from zero. Similarly, if we just have that magnetic field is a function of time, this means that we can expect some electric field induced, which will be different from zero. Now, this type of direct relationship between the electric field and magnetic field, we call this coupling. So these fields are coupling, and I want to ask you, where was the last time you heard about coupling as a concept? So, when was the last time you heard coupling? I believe that many of you in the class might remember that in linear algebra, you have considered the solution of systems where the relevant equations that can be described in the form of a matrix. In the matrix, the most important aspect that can be used is the use of diagonalization of data or of vectors. And when we do the diagonalization, what we are in principle doing, we are decoupling. So we can have several variables which depend as a function of time. We want to decouple them. So in some way, decoupling means to represent the problem in new variables such that the electric field can be only as a function of the electric field and not also of the magnetic field. As a reminder, which can serve as support for your future courses, but also try to connect with the principles that you have learned in linear algebra. And you should learn this better. I can represent the following. So the rate of electric field, this can be equal to 3 electric field minus 2 magnetic field, and the rate of change of the magnetic field as a function of time can be equal to minus some electric field plus 4 magnetic field. Okay, so here what we observe that of course these equations don't mean much. Okay, of course there could be some coefficients here. So here it looks like the coefficients are 3 minus 2 minus 1, 4. So this is our mixing coefficient. 3 minus 2 minus 1, 4. This is a 2 by 2 matrix. It represents how they are related. That's good. And the problem is that often we want to decouple the system so that we can solve the problem in an easier way. Now, this decoupling, in fact, we're going to see this one in the future weeks in this course, because we will see how we are going to select specific relationships between the vectors and these, not vectors, sorry, potentials. And we have, this is one of the potentials, which is the potential of the magnetic field. And if we take the derivative with respect to space, so let's consider this one, d over dx, what do we get from A? If we take the derivative d over dx. And similarly, if we get d over dx, what would we get if we take the derivative this way? If we take the derivative with respect to space parameter here, we get the magnetic field. So this is the potential of this, and this is the potential of the electric field. So we get these vector quantities. Now, why do we mention this one? We mention this one because often in order, not often, well, in quite a few different settings, we can establish certain relationships between these two potentials in order to have a more elegant solution for the differential equations where we're going to find the E and the B. Okay, so these concepts, as electronics students, we're going to see each other again in third year. I just want you to be very clear of what the principles of coupling and decoupling mean, or at least starting from the fundamental aspect that even what coupling really is. Good. Now, the last time we talked about the inductance. We talked about in the future about the capacitors, and now what is essential is that often in these systems we are generating energy or we are wasting energy. And the energy, often, it is, well, energy is measured in joule, for sure. So in order to get the energy, which is measured in joule, we may need to integrate the power, which is measured in watt, and we need to integrate this one over time. And the power in watt, this is equal to VI, okay? So if we know the potential difference in a specific construct, we can multiply it with the current that flows in the system, and we find the power. This much, we are very good at this. We can easily figure out how we can relate the power with the energy. Now, and then what we are going to see is that often we use electromagnetic systems to do work. For example, we can apply a change in magnetic field in a system, and we can make possible the rotation of turbines from multiportoare, përtërtuar turbina, përtërtuar sisteme, duke ushtruar forcë, e cila në princip ka gjenerimin e forcave ose e diferencave potenciale si funksion I diferencës së fushave për njësi të kohës. Pra, so here, if E is a function of time, that means that we get some induced magnetic field, and here, if the electric field is changing as a function of time, this means that the flux of electric field over some area, this is going to be different from zero, and also the rate of change, so let me also write this one, d over dt is equal from zero. Similarly, I'm doing a jump from this principle to here, so this means that we're going to have a rate of change of the magnetic flux d times dA. So we'll find the derivative of this one. This will be different from zero, and we shouldn't forget that the magnetic flux is equal to the integral of the magnetic field over some area. So if we rewrite this again, sorry, this belongs to one set of logic, but here I'm going to rewrite again what we see here, which will be the following. The rate of change of the flux as a function of time, this is going to be different from zero. The moment this rate of change of flux as a function of time is different from zero, we have an EMF, which is going to be produced. Now, the thing is that if we have some electric field which exists over some specific distance, so if we have some electric field different from zero, we can integrate that one as a function of length, and so what I'm saying right now is the following. What is EDL? This EDL is equal to some potential difference, and sorry. I'm just thinking for a moment, and what we can give for the moment as let me think. Now, there are different ways how to explain this one. I can choose at least 3 or 4, but let me start, at least for today, in this way. Let's try to make this one as much intuitive as possible. Let's assume we have a wire which which is connected to a resistance, and then we can put over these wires, we can put a conductor, okay? And this conductor can move back and forth. Now, at the same time, let's assume that we have some magnetic field which is pointing into this circuit. And we may be interested into calculating what is the magnetic flux over this closed circuit, because these are wires, this is the resistance, this is the conductor. And at this point, let's also assume that this length is equal to L, and this distance, this is equal to X, okay? So, and let's assume that this is the coordinate system, this is Y, this is X. So, this is the position of this one with respect to the zero, it's X. Then we can find the following quantities. What is the area? The area, it is equal to L times X, okay? This is the area. And what is the magnetic field? Magnetic field is equal to B, or let's write it like this. Magnetic field B, it is equal to B times minus AZ, okay? Because the way we draw this one is pointing into the board. Then we need to find the flux, and the flux is equal to the integral of B dot dA. If the magnetic field is a constant value, we can take it out of the integral. This is what we do with constants, right? We take it out, and we get that this is equal to B times the integral of the area. Integral of the area, we know that these are inverse functions of each other. This means that we can cancel these two. The integral of the differential is equal, they are inverse functions, and finally, we can say that the flux is equal to dA. And at the same time, flux would be dLx, okay? So this is the flux. And then we can try to find, let's assume that if this bar is moving with some velocity v, okay? If this bar moves with some velocity v, we can say that the flux, the magnetic flux, as a the rate of change of magnetic flux as a function of time, it can be described as the derivative of BLX over dt. Now, in this BLX over dt, we have a couple of terms which are constant. The terms that are constant, it is B and L. So here we are, and the rate of change of flux as a function of time, this will be equal to BL times dx over dt. Now, so we see that x is a variable quantity, which means that let's think for a moment. Well, this means that this is going to be the velocity. So this is going to be BL times the velocity. Now, if we notice the units of this quantity that we just determined, we notice that this has units of volt. Here, let's write an equivalent sign. It's not equal, but we just want to say that this whole thing, it is equivalent to something which is measured in volts, which means that this can serve as a power supplier to these circuit components, which means that we can have a current I, which can flow in either direction. So it can be the current in red or the current in green. Now, so this is one way to talk about this possible induced current in this circuit. That's one. The second possible way, which can all help to get a larger picture, is the following. We know that the force on a charge, it is represented by the Lorentz force, which is equal to force is equal to Q times E plus the charge times the cross product between the velocity and the magnetic field. Okay, so here we have a force equation. And then let's try to electric field, we have none. There is no electric field at all initially. So this is zero. This is gone. Okay. And then let's just check what is happening with the force in this moving bar, okay? Because only those charges in that moving bar, they have a velocity equal from 0, meaning that, for example, if you have one electron which is sitting here, if we draw it like this is the electron, the force over this electron, it is if it is stationary, the force will be 0. But let's assume for a moment the positive charges on this bar, the force on those will be the following. This is going to be Q times the velocity, and velocity it is equal to V times AX, okay, assuming that the velocity is moving to your right side, cross product with the magnetic field, which is B times minus AZ, because this is what B was, okay, as we denoted this here. And we notice that what is A cross AZ? AX cross AZ, who can answer this? Çfarë drejtimi ka kjo forca? You can have a look at the chat section. AX, AY, AZ. If you rotate clockwise, we always get plus. Now here we have AX times minus AZ, so we are moving counterclockwise. We should get a negative sign, but here we have another negative sign. So the cross product between these two is going to be QVB times AY, plus AY. So apparently, we're going to observe a force which moves this way. If the force on the positive charges forces them to move this way, that means that the correct direction of the force along the wires will be the current in red, okay? Not the one in green. So we notice that if we have this current I, then we can see that we can determine a current density J, which is I divided by the area, which has units of ampere per meter squared. And then we also know that J, it is equal to sigma times E. So if J is different from 0, we can divide by the conductivity, we find the electric field. So this is another way to represent or to prove that we can have an electric field which will be generated over the system the moment that we have a mechanical motion of conductors or components that carry charges, that they can have positive charges and negative charges. So this is the second way, okay? And we see that these volts, pra ne intereson që përdojnë ca volt, por është madhësi që madhe dhe volt, çfarë është kjo, është diferencë potenciale, let's make use of it. That's what we are doing, okay? And in principle, now we can report the following. If we have a conductor which is moving with respect to magnetic field, we are going to observe an EMF. This is d flux over dt, okay? And this d flux over dt, initially we can write just this. So this is what we care. But what is also important for us, often it is very important to determine what is the direction of the EMF, okay? Which means that what will be the direction that the current is going to be applied. So, of course, this is very important. And the possible options in this expression is that it could be either plus or minus. And when we say that it's either plus or minus, for the moment, let's write it like this, plus minus. We have to pick one. Now, the correct solution is minus. Okay, this is how it should be. But again, as we said before, it is sometimes good to use our intuition into being able so that we can choose which one is the correct one. Is it the positive one or the negative one? Okay. So this is the EMF which we are assuming that exists in a system. And for a moment, we can think, and by the way, so let's think for a moment, if this is true, this is the general equation. Okay, let's stick here, and we have not selected yet before between plus or minus. But in this construct, we have that the EMF is equal to dlV, the magnetic field times the length times the velocity. Now let's have a look at a different system. This different system, which we can consider, is that let's imagine a disk which is rotating. Okay, so we have a disk which is rotating with respect to its center with an angular velocity omega radian per second. And this system, we also have a magnetic field. You can see this part, magnetic field, which will be equal to B times AZ. Okay, so this is the magnetic field, and what we can do is that we can connect. So if this is in motion, we can use a wire with a spring that is touching the outer edge of the rotating disc. So we just need to touch it. We cannot fix it because the wire it will be wrapped out or wrapped around the disc. So you just imagine that you're making a connection to a circuit from the outer side like this. You are pushing like this. That means that you are creating a current. At the same time, you can also make with a spring system. You can touch the bottom of the center here. So at least you can make connections with systems that are in motion, and then we can connect here another resistance R. And the question is the following: is it possible to have some R? So this is the question. What we can see here is that, first of all, we can expect the following. We are going to have a flux over this disk. Okay, Kenyan disk, we have a flux that is changing. So immediately we could say that using this principle that we discussed up to this point, we can say that we are going to have an induced EMF. So I'm just saying this. Analyzing the flux, we should have some induced EMF, electromotive force. So we spell it this way: electromotive force. So this one is different from zero. That's the first idea that we can use to conclude that this is different from zero, and then we're going to have a current. The second aspect is the following. When we say the following, is this discussion of the force. So if we have positive charges and negative charges in this disk, all of these will move with some velocity. So let's assume here we have some positive charge right here. And this is rotating. That means that this is going to have some velocity. And by the way, what is the velocity? The velocity, it can be described, V, it's equal to V times what? Times AR, okay? Because these charges will be moving across this path, a circular path. And which means that we're using a coordinate system R, phi, Z, which is the cylindrical coordinate system. Now, at this moment, we can, let me think for a moment, dr force times dr, okay. Volts, yeah. So if we use the analysis of the force, we can say that the force is equal to QVB. The force per unit charge, which is equal to force divided by Q, it will be equal to VB. Okay, and the EMF, this in volts, this will be, this can be described as the magnetic force integrating this over the R. So here we can have VB times dr. So this is how we can calculate the induced EMF, assuming that we are analyzing this configuration based only on the force and not the flux. So here, this integral, let's integrate this one from 0 to A, assuming that the outer radius of this disk is equal to A. Then we just have to write down what is the velocity. Velocity here, we know that it is going to be equal to omega r. Okay, this is the velocity in rotating systems. If radius is 0, that means that we are at the center, the velocity will be 0. So we get here omega r times b times dr. This will be equal to omega, it's a constant. B is also a constant. So this should be omega times b. R dr, it is equal to r squared divided by 2. So this is r squared divided by 2. The limits of integral from 0 to a. So overall, we get an EMF, which is 1 over 2 omega b a squared. So if this is the induced voltage, then the current would be equal to the electromotive force divided by the resistance. So finally, we get 1 over 2r omega b a squared. So here, we notice that if the omega, or if the rotational speed is higher, we are going to get a larger current. Okay, so we found the EMF for two different constants. This constant that we are just erasing, what did we have? We had a conductor which was moving, changing the area, the effective area of the circuit. Here, we're not changing some area of the circuit, but we are having a rotating disc as shown on the figure. Yeah. Actually, I wish I did not erase this example we have here, but it might be worth analyzing this one a little more in detail. So let's assume that this is the conductor that is moving with some velocity. As we drew before, we noticed that there was a current like this, in case the magnetic field is pointing into the board. Now, So let's assume this system like this. This is sitting, it's not moving at all. Then we give it a kick, we kick the conductor, and this starts the motion with a velocity v0. And then, what was the information that we know so far? The induced electromotive force is equal to BLV. The current is going to be equal to BLV divided by the resistance R. And the first possible question that we can construct is that we need to find what is, we found the current. And then the second question is trying to determine what is the force on the bar. Okay, so we found the current. This is A. B. Force on the bar is equal to what? So the force on a conductor, this can be written as so the force is equal to, let me think for a moment, is ILB. So it should be equal to the, let's see for a moment. So, because, and in fact, this force, it is generated because once the current starts flowing, okay, once this current is different from zero, we're going to have positive charges which are moving upwards. Okay? As these positive charges move upward, these charges move upward because the EMF is created, and the EMF it has to happen along this wire. Okay, so there is no other way where these charges are going to move. We cannot expect this wire to move out of the conductor and to move away to the left or to the right. Okay, so the EMF sets into motion positive charges in the single possible direction. But at the same time, once we have this motion upwards, we are going to assume that the force is still equal to QVB, and we use the right-hand rule to find the direction of this force. the right-hand rule, it points that the velocity being up, the magnetic field pointing into the board, and we find that the magnetic field is going to point along the, let's write it like this, QVB minus AX, okay? So this is the direction of the induced force. So if we have this force, then we may be interested into writing down how, so it looks like if this conductor, it starts moving to your right with a velocity v0, we may want to determine how this velocity changes as a function of time. And then to do this, we have the equation of motion. Equation of motion, it is Newton's second law, which we know, and it's written like force is equal to mass times acceleration. And if this is mass times acceleration, we can see that this is ILB, and then let's write here ILB, instead of the I, we can write the following, VLV over R, this is the current, times L, this is the second element here, and this is, sorry, ILB, I, we wrote it, L, we wrote it, this is B, and this is equal to M times A, that's good. So the acceleration, this can be written as BL squared V over R, okay? So this is the acceleration. Then, if this is the acceleration, we can also try, so wait a second, so this is force, we have the force, this is the acceleration, and the question can be the following. What is the velocity as a function of time? To find the velocity as a function of time, we just need to implement this equation again. So we get this, the force, which was equal to I over B. But we have a mistake here. Can you see the mistake? A. We have to divide here by the mass, okay? To determine mass, chiedzimy citimi. Then the force here, force is equal to mass times dV over dt. So we get B squared L squared times V divided by R. This is dV over dt. Then we divide both sides of the equation by dV, or no, let's divide both sides of the equation by the velocity. 1 divided by velocity, this cancels out. We multiply both sides of the equation by dt, like this. So this dt cancels this, and then finally we get the integral of dV over V. It is equal to, let's consider that this is a constant, okay? And by the way, we have to include also a negative sign here actually. We need to put a negative sign because the acceleration, it is reducing the initial velocity. So we are trying to decelerate it, and this means that this is going to be equal to minus k dt. And so this is our new differential equation, where k, it is equal to, wait a second, so this is, let's divide here m, k is equal to b squared L squared over mr. These are all constants, okay, they're not going to change. Then we integrate both sides, we find that the ln of the velocity starting from v0 to 0, this is equal to minus kt. Then we take the exponential of both sides, so this is exponential, this is exponential, then we get exponential of ln, this is v, wait a second, from V0 to 0, V will be then equal to V0 times exponential of minus kt. So apparently, this is how the velocity is going to change. It is an exponentially decreasing, what do we call this one? It's an exponentially decreasing quantity. Now, for a moment, so now that we know the velocity, we can have a look at this current, and this current will be equal to BLV. B is a constant, L constant, R is a constant. Instead of the velocity, we can write the velocity, which is a function of time, minus kt. So it looks like even the current is a function of time. So at this stage, we can, if this is the current, we know that the power is equal to VI. And if this is VI, we can also write this one RI squared. Okay? So if this is RI squared, we can find the total energy that can flow in the system from 0 to infinity. So here we can say that the total energy in the system can be equal to the integral of R times I squared. What is I squared? This is going to be B squared L squared over, wait a second, I have a mistake here. What is our mistake? We will divide here by R. B squared L squared divided by R squared times V0 squared e to the power minus 2 kt dt. Yeah. So this is how actually we can find the total energy which is spent in a specific system. Now you can integrate this expression, and then what can be interesting is to compare. You can try this as a homework. Compare this result we obtained here with the total kinetic energy that the system had initially when it started with a velocity v0. Do you have any question?
Yes.
Yes.
Can we have a 5-minute breaks, please?
Yes, I was planning to have a break. That's true.
Thank you. Thank you.